Hello, future engineers. This is part 2 of 3D rigid body equilibrium problems. If you appreciate my effort of providing you contents in statics that have so many problems, I designed it so that it will be considered as a one-stop channel. Then please share my videos, like, and for those who haven't yet subscribed, please subscribe because that will inspire me to do more contents for engineering courses, especially civil engineering. And I hope that you will become great and better engineer in your chosen field. The uniform I-beam has a mass of 60 kilograms per meter of its length. Determine the tension in the two supporting cables and the reaction at D. So we have the uniform I-beam here with length 8 meters long, supported at D 1 meter from one end. And we have cables that are symmetrically placed. Therefore, we expect tension in AB to be equal to that of tension AC. And this is the loading, which is 60 times 9.81 in newtons per meter. So the vertical component of tension AB is tension AB times 3 divided by square root of 2 square plus 3 square, or square root of 13. We multiply it by 2 because tension AC is also equal to tension AB. So this vertical tension is 2 times tension AB times 3 over square root of 13. And to solve for tension AB, which is equal to tension AC, we set moment D0. Let's call that reaction at D. So moment D0, or summation moment about D0. So we have 2 times tension AB times 3 over square root of 13 times 5, then minus 60 times 9.81 times 8 times 3, because the center is 4 meters from the other end and this is 1 meter. So 60 times 9.81 times 8 times 3. So we can now solve for tension AB, which is equal to tension AC. And it is 6098 newtons. Likewise, we set moment A0, or summation moment about A0. So we have RD times 5, then equals or minus 60 times 9.81 times 8 times 2, because this is already 2. So 2 meters from the center. So 69 times 9.81 times 8 times 2. So RD can now be computed. It is equal to 1884 newtons. The light right angle boom, which supports the 400 kilogram cylinder, is supported by 3 cables and a ball and socket joint at O. So remember, ball and socket joint, there are 3 component reactions attached to the vertical XY surface. Determine the reactions at O and the cable tensions. So let's draw the free body diagram first for the reactions. And we have tension BE. And these tensions here, we write them in vector form so that we can compute the components. We can tell the components. So this is the weight, 400 times 9.81 newtons. So tension AC is along X negative 1, along Y positive 1, and along Z negative 2. So it is magnitude of tension AC, quantity negative 1I, positive 1J, then negative 2K. This is the Z-axis. Divide by square root of 1 square plus 1 square plus 2 square. So it is tension AC over square root of 6, quantity negative I plus J plus 2K. Then this is the X component. in the negative x direction, tension AC over square root of 6, then y upward, tension AC over square root of 6, then along z forward rather, 2 tension AC over square root of 6. Negative 2. Negative 2. So, tension BD is tension BD magnitude times quantity 2J, the negative 2K, over square root of 2 square plus 2 square. So, tension BD is tension BD magnitude J minus K over square root of 2. So, Y component upward, tension BD over square root of 2. J component backward, because that's negative, tension BD over square root of 2. So, set moment x 0. So, by right thumb rule, 400 times 9.81 times 2, then minus 2 tension AC over square root of 6 times 1, minus tension BD over square root of 2 times 2. So, simplifying, tension AC over square root of 6 plus, after we cancel out 2, plus tension BD over square root of 2 equals 3924. Call that equation 1. Then set moment Z0 along here. By right thumb rule, then we have tension AC over square root of 6 times 1. This is the positive sense of moment about Z. Then minus tension AC over square root of 6 times 1. This one, the vertical component, it's minus. Then plus tension BD over square root of 2 times 1.5. Then minus 400 times 9.81 times 0.75. So we can cancel these first two terms. They're equal but can be cancelled. Then we can compute tension BD. Tension BD is 400 times 9.81 times 0.75 times square root of 2 divided by 1.5. And it is equal to 2775 newtons. Substitute this value into equation 1 to solve for tension AC. So tension AC over square root of 6 plus 2775 over square root of 2 equals 3924. So tension AC can now be computed. It is equal to 4,805 newtons. Then we set moment Y0. By right thumb rule, positive sense would be that. So tension BE times 1.5. Tension BD over square root of 2 times 1.5 plus tension BE also times 1.5. Then minus this one. The other two are not involved, parallel, and it passes through the y-axis because these points lie on the same xy plane. So minus 2 times tension AC, 2 times 48 tension AC over square root of 6 times 1. So substitute the computed values. So 2775 over square root of the 1.5 plus 1.5 tension BE minus 2 times 4805 over square root of 6. So tension BE is equal to 653.3 newtons. And for the reactions at O, Rx0, so we have OX minus tension AC for 805 over square root of 6. That's the only equation. So OX is equal to 1962 and it is directed as shown. Ry equals 0. So OY plus tension AC, which is 4805 over square root of 6, plus tension BD over square root of 2 plus 2775 over square root of 2 minus 400 times 9.81. So OY is 0. And RZ equals 0. OZ equals OZ minus 2 times tension AC 4805 over square root of 6 minus tension BD 2775 over square root of 2 minus tension BE, which is 653.3. So OZ is 6539 newtons. So that's it for this problem. The 100-pound uniform square plate is supported by a ball and socket joint at O, a cable at E, a fixture A which can support vertical force only, and a linear spring at C. This is the spring. If the unstretched length of the spring is 6 inches, determine the spring constant K required for equilibrium in the position shown. So let's have the component reactions at O, because it is a ball and socket joint, so it is complete. Then the weight, 100 pounds at the center. The square plate is 36 by 36, so it is 18 inches from AB and 18 inches from AD. Then tension and force in the spring. And vertical reaction at A, as mentioned. Then tension EF in vector form is magnitude of tension EF along X negative 18I, along Y negative 20J, because the plate is 36 inches and that's 16 inches. So I mean to say from E, move backward along X 18 inches, negative 18I, along Y to the left negative 20, that's why negative 20J, then upward 16 inches, positive 16K, over square root of 18 square plus 20 square plus 16 square. So TEF is equal to magnitude in decimal form negative 0.575 I minus 0.6389 J plus 0.5111 K. And the components are as shown. And this is the force in the spring, K times delta S, where delta S is 10 inches minus 6 inches. So delta S is 4. So this is the X component in the negative direction, the Y component to the left, and the Z component upward. So first moment about OX0 to set up equations for TEF and AZ. So for these tension components, positive moment is in that sense by right thumb rule. Then the 10 pounds is here, 100 pounds is here, so it's negative. AZ is also negative moment about OX. The distance of the 100-pound force is 6 inches from OX, so that 12 plus 6 is 18. Remember, it's at the center. So equals 0.5111 TEF times 24 minus AZ times 12, this 12 here, then minus 100 times 6, where 6 is 18 minus 12. So simplifying, 0.511 times 24 TEF minus 12 AZ equals 600, equation 1. Next is moment about OY equals 0, so that it involves the same unknowns. K delta S will not be involved because O and C are on the same horizontal plane. So K delta S passes through the OY axis. It has no moment. So same is true with this component and this component, parallel, and this one passes through OY, same plane. So only this vertical component of tension has moment about OY. And by right thumb rule, it is positive, AZ is positive, 100 is negative. So 0.511 TEF times 12, 12 only because O is 6 inches from CD. So 18 minus 6 is 12. So 0.511 TEF times 12, not 18, 12, plus AZ times 30, 36 minus 6, so 30. Then minus 100 times 12, where 12 is 18. Take note, it is 18 minus 6. So 100 times 12. Simplifying, 0.511 times 12 TEF plus 30 AZ equals 1,200. Solving these two equations simultaneously by elimination, substitution, or whatever method you apply, then tension EF is 73.37 pounds. Then that's the only value that we want. And AZ is 25 pounds. Finally, we set moment OZ0. So delta is 10 minus 6, so 4 inches as mentioned. MOZ equals 0. So the positive sense of moment would be this, like that. So positive would be 0.63989 TEF. 0.575 TEF will all be positive, and negative will be K delta S. So beginning with 0.6389 TEF, the moment arm is 12 because 18 minus 6 is 12. This is also positive about OZ, plus 0.575 TEF 73.37 times 24, and minus K delta S times 24. Minus K times 4 times 24. So the only unknown here is K. We can now solve for K. K is equal to 16.41 pounds per inch. So that's it for this problem. The uniform 15 kilogram plate is welded to the vertical shaft, which is supported by bearings A and B. Calculate the magnitude of the force supported by bearing B during application of the 120 Newton meter couple to the shaft. The cable from C to D prevents the plate from turning, and the weight of the assembly is carried entirely by bearing A. Because the shaft at A is large, so that's why the weight is carried by that uh, bearing A. So we have 15 times 9.31 at the center for the weight of this plate. Then reactions, tension at C and D. Let's have this orientation as our guide. So tension CD is magnitude of tension CD going to X 0.2, 0.2 meter, then along Y negative 0.6. So 0.2I, positive 0.2I minus 0.6J over square root of 0.2 square plus 0.6 square. In vector form, this is tension CD magnitude I minus 3J over square root of 10. So the X component, which is in this direction, is tension CD over square root of 10. And the Y component is in that direction, 3 tension CD over square root of 10. Then at B, we have BX and BY only. At A, we have 3 reaction components, AX, AY, and AZ, where AZ is the weight of the system, which is 15 times 9.81 as mentioned in the problem, and AX, AY. So to solve for the tension in CD, we set moment about AZ axis or AB, 0, ABZ or AB. Then the positive sense would be that sense, 100 equals 120 Newton meter. Remember, this is Newton meter. So the moment arm should be in meter to be consistent. So minus tension CD over square root of 10 times zero point 0.6. So that's the only equation. No more. All these forces are not involved. 15 times 9.1 not involved because it is parallel to ABZ. So tension CD can now be computed. It is equal to 632.46 newtons. Then moment about AX, AY first, 0. By right thumb rule, positive sense would be that sense. So BX is positive. BX times 200 equals BX times 200. Then 15 times 9.81 passes through AY axis because this vertical axis and this vertical plane lie on the same plane. So it passes through. Then minus TCD over square root of 10, 632.46 over square root of 10 times the distance is 400 plus 80 plus 200. So that is 400 plus 80, 480 plus 200, 680. So from there we can solve for Bx. Bx is 680 newtons. To solve for By, we set moment Ax about Ax 0. So by right thumb rule, because this is the positive x-axis, positive sense would be that way. So By is considered positive. So equals By times 200. Then minus Ay, Ax. So parallel minus 15 times 9.81 times 300 mm. Then minus, this is also minus 3 tension CD 3 times 62.46 over square root of 10 times 400 plus 80 plus 200. So again 680. That distance is 680. So the only unknown here is By using your calculator. By equals 2261 newtons. So finally we can solve for the force at B. Square root of 680 square plus 2261 square. BZ is 0 of course because it is mentioned the entire weight is carried by bearing A. And it is free to slide also here. So FB is 2361 newtons. So there's no BZ reaction because it is already mentioned that the entire weight is carried by bearing A. So bearing B will no longer carry portion of the weight of the system. The spring modulus of modulus K 900 newtons per meter is stretched a distance delta 60 mm when the mechanism is in the position shown. Calculate the force P minimum required to initiate rotation about the hinge axis BC. This one, when P is applied, it tends to rotate, and when that initiates rotation, this end of the bar at D will tend to rotate in that direction. So the minimum required P to initiate rotation means there will no longer be contact at D for that case. So there's no reaction at D when P minimum is required to initiate rotation in BC, along BC, or about BC. And determine the corresponding magnitudes of the bearing forces. at B and C, of course, which are perpendicular to BC. So along BC, no force. It's free to slide. That's why there's no force, friction. There's no friction, although it's not mentioned here. But it is mentioned that the forces at the bearings are perpendicular to BC. What is the normal reaction force at D if P is P minimum divided by 2? So if P is half of P minimum, then the system, this mechanism will not rotate. So that's why there is contact between this support and D when P is half of P minimum. So let's answer first the first question on P minimum and the corresponding bearing reactions at B and C. So we set moment BC 0. By the way, let's apply the component reactions at B horizontal and B vertical. We have C horizontal and C vertical. Then RD, which is 0 at the first when P is P minimum. And we have here tension in the spring, which is equal to 900 times 0.06, which is equal to 54 newtons. So if we sum up moments about BC, then we can solve for P minimum right away. Remember, RD is 0 for that case when P is P minimum to initiate rotation. Moment BC 0, and therefore P is positive, 54 is negative. All these forces are not involved, and remember RD is 0 in the first part. So it is equal to P times 135 and minus 54 times 45. This 45 here or this 45 here. 54 newtons is 45 mm below the plane of BC. So from there we can solve for P, which is equal to P minimum, and it is equal to 18 newtons. Then let's solve for B vertical by summing up moment about CH0. By right thumb rule, B vertical is, this is your right thumb, so the curling of your fingers would be descends. So B vertical is positive. The distance is 165 plus 135. So equals B vertical times 165 plus 135. BH is not involved, parallel to CH. Then minus P, 54 is also not involved, parallel to CH. So minus P, the distance is, take note, this is 55, this is 40. So meaning to say the distance of P from BH is 15. 55 minus 40. 15 plus 165 plus 135. So 18 times 15 plus 165 plus 135. So those are the only forces involved. So we can solve vis-a-vis equal to 18.90 newtons. Then likewise, summation moment BH or moment BH0 to solve for vis-a-vis. So by right thumb rule, CV is positive. The positive sense is in this manner. So CV times 135 plus 165 or 300. Then minus P times 15. Minus 18 times 15. Where 15 is 55 minus 40. So vis-a-vis is equal to 0.9 newtons. And to solve for CH, we sum up moment about BH. Let's solve for BH first. We sum up moment about vis-a-vis. Moment vis-a-vis 0. By right thumb rule, BH is positive. This is your right thumb. Curling of four fingers would be that sense. Positive sense would be that manner. So BH times quantity 165 plus 135. Then minus 54 times 135. So 54 times 135. So BH is equal to 24.3 newtons. So from there we can solve for FB, square root of 24.3 square plus 18.9 square. So FB is equal to 30.78 newtons. And to solve for CH, we set moment vis-a-vis 0. So positive sense would be 54. Positive moment would be this. If the right thumb is pointing upward, curling of four fingers would be in this manner. So 54 times 165 equals 54 times 165 minus CH times 165 plus 135 or 300. So CH is equal to 29.7 newtons. So FC, square root of 29.7 square plus 0.9 square. So F sub C is equal to 29.71 newtons. Finally, when P is P minimum over 2 or 9 newtons, we can now, there is reaction at D. So RD is now involved in our moment summations about BC. So this, remember this is 9. So 9 times 135 equals 9 times 135 plus RD times 90 and minus 54 times 45. So solving for RD is equal to 13.5 newtons. So that's it for this problem.